Hey everybody, it's Armin again. So this video is a continuation of the previous one where we were discussing the several different heat exchanging oil coolers that I've been doing tests on. So I ended up performing this series of tests twice. I'll go over all of the experimental inputs and then we'll go over all of the experimental outputs, as well as I'd like to go over how my calculator is designed. But we'll do that last because I don't know if many of you actually want to see all of that stuff. It's heavy in the engineering and mathematics side. But for those who are in for it, I'd love feedback. Again, all of this stuff is to the best of my knowledge and the best of my abilities, as I am a degreed engineer, but again, I don't have any background in actual heat experimentation or design or anything. So all of my knowledge does come from my classes that I took in college, thermodynamics and heat exchange classes, heat transfer, as well as my experience, my actual experience in automotive, knowing how a lot of this stuff works, and of course my stack of books and other people's experiments that they've done on similar type systems. All the information given here is subject for debate, but I'm giving a review and synopsis on my results that I've achieved. With that said, let's get on with the fun stuff. Alright, so let's discuss how we set up our test. First, we hooked up our water pump to our heat exchanger assembly, and then we bled all of the air out of it by holding the heat exchanger in the position where both ports were upward. This got all of the air out of the system and made sure it was empty. Then what we did is we used the system with the water pump set at the correct voltage input, and we put it into the metered bucket to see how fast it filled the bucket up from the 1 gallon marker to the 2 gallon marker on a stopwatch. And we used that as our flow. So that was our measured flow of that system as assembled. We also wrote down what amperage the power supply was showing on the screen, because these show how much amperage is being pulled at the voltage input set. And that was used for, that was all just so we could have some comparators later on. Next, we took the fan and assembled the whole assembly together. And at the various settings, so in one of the experiments it was 8 volts, 12 volts, 16 volts. We set the fan to 8 volts. We measured the average velocity several times across the heat exchanger to see what our average air velocity was. And then we did that for each of the settings until we got consistent enough numbers that we were confident in. After all that was done, we turned on the turkey pot, we turned the fans off, and we let the water pump just continue to cycle until we saw the data on the screen of approximately 90 degrees Celsius. Then we were able to start the actual experiment. We hit record, all the data started moving around, and once it stabilized, then we were able to actually, we waited for it to fully stabilize to where we saw all of them sort of moving together or converging, whatever it was, and then we stopped recording. We changed to the next set of settings. Now I'll explain. Since we were running each of these exchangers at 3 fan speeds, it was slowest fan speed, then the next fan speed, then the next fan speed. On the first series of experiments we did, it was first pump speed, 3 fan speeds, then restart with second pump speed and 3 fan speeds. So you got 6 results. Alright, so that's how we set all of them up. Let's actually go over the data now. So let's actually discuss some of the data here. What we're looking at here is the first experiment data. This is the 19-row traditional. We're looking at the input voltage to the fan. So we see 6 volts is what the setting was, and it pulled about 2.2 amps. There was some variance on it, so we just watched it to see where it mostly was hanging out. We measured a 2.4 meters per second air velocity across the face of the heat exchanger, and then we move over here, we see we have our input voltage to the pump, which was 10 volts. It pulled 5 amps almost on the dot, and we got 3.53 gallons per minute measured. The temperature measurements that we took, this is all a snapshot in time, so it was these input temperatures from the air. So the air input was 37.1, that's pretty much ambient air, and then the air leaving the exchanger was the 73.5. On this side, we see the water. So the water entering was 89.7 degrees, and the water leaving was 85.8. And then over here is the calculated output. So the K-factor doesn't change. The K-factor was strictly based off of the physical measurements, so that's going to be the same for all of these. It's just 50.5. So 50.5% of the frontal area of this heat exchanger is airflow. The CFM approximated from this data, the 2.4 and the rest of the data here, is approximately 152 CFM. So with all that data, we end up seeing that it was pulling 308 watts. The effectiveness value came out to 7.4%. The UA was 10.6, and the U value was 7.3. So a fun piece of detail here is that if you look at the first 19-row traditional versus the 25-row traditional, you'll notice that we have a 24 for the U value versus a 20 for the U value of the 25. So that indicates that the 25 row is actually a less efficient design, but it does have larger cross surface area, so it ends up with a higher UA value. So it still comes out with a 38 as the UA, while this one comes out with a 35. And then we move down to looking at the data for the other ones, and you can see that they have exceedingly high values for the U and UA values comparatively to the traditional ones. Now you will notice that we don't have any data for the 25-row dual pass, and that is because we had so much issue with testing the 19-row dual pass. It was cooling the fluid off so fast we wasted a lot of our time having to wait for reheating on that unit. So we ended up not doing that test. I figured I would wait to get all of my data together and see how the experiments went before going and doing that. So we did the whole experiment all over again. This time, as of looking at the data, we realized, you know what, the water is such a limiting factor that having multiple pump speeds doesn't do anything for us. So we'll just perform the test on 3 different fan speeds. Also, we weren't really confident in the 6-volt fan speed because it was even showing us various values for average airspeed. So we went ahead and bumped it up to 8 volts, 12 volts, and 16 volts, as opposed to the previous tests 6, 10, and 14 volts. And that provided us with what seems to be better data. Now, running all these through the same calculator, we got new values. So up on the screen now, we're looking at the secondary set of experimental data. Once again, the 19-row traditional, at the highest value of fan speed, it pulled the best values. So we were looking at almost the exact same U and A values. First experiment showed 24 for the U and a 35 for the UA. So that shows us almost dead on they were the same. And then we pop down here and we see that the large dual pass and the 19-row dual pass obliterated the competition without question. You can pause if you want to read over it all, but we can summarize from this information that without a doubt the 19-row traditional is a more efficient design than the 25-row traditional, but of course you go to bigger because there's more area, even if it is slightly less efficient of a design. But the large dual pass is exceedingly efficient, and so is the 19-row dual pass. So we can surmise that the 25-row dual pass would be absolute king in all 5 of these, out of all 5 of these that we've tested here today. Alright, so this is the fun part of the video. This is where we actually go over how the calculator works. I've enjoyed being able to share this with some of you already because it has allowed me to see where I've made errors or things that I can improve. Those are 2 separate things. There can always be more improvements made to the calculator, but this is what I've come up with, and I'm really happy to say that the data has revealed results that look very reliable. And I say this as the fact that the first set of experiments with the not so great of data has shown to have the same outputs almost as the second round. As well as there are 2 methods of calculation in here, so at the end we're able to see if one method achieves the same numbers as the second, and that can be used as a verification means. So let's go ahead and dive on in. Currently what's up on the screen is the calculation for the large dual pass on the second set of experimental data for the highest fan speed. So up here, you'll see I have subscript H and C refer to the hot water and the cold air, respectively. So it's the hot fluid and the cold fluid, as they say. And the subscripts I and O are just inlet and outlet. So you'll see here we have T, C, I, which means the temperature of the cold fluid, so the air, and inlet. And over here, thanks to my math CAD teacher for all the calculations in college, you always label your stuff over on the right side so people can read this. So we have temperature in, temperature out of the cold fluid, temperature hot in and temperature hot out. For hot fluid, of course, we have the velocity of the air and the gallons per minute of the water. Next, we move to the physical dimensions. These are what I've measured off of the heat exchanger. So all those are the inputs. That's pretty straightforward. Next, we move to the dimensional analyses. So this is where we get the gross cross-sectional area. So how big is the front of the exchanger total? How much area of that is the fins? How much area is that is the plates? And then what is that net for cross-sectional area? You divide the net over the total, and then you get your K-factor. So our K-factor for this one came out to be 58.406%. Next, we need to determine the surface area for the fins in the cold fluid. So we have 2 times the facial cross-sectional area plus the rest of the profile of the fins. Next, we have the fins in the hot fluid. Well, this doesn't have any fins in the hot fluid, so it's not considered. This line item is only used for the 19-row dual pass and the 25-row dual pass. Next, we have the surface area for the cold fluid. This is actually for the plates. So you'll see we have number of plates times the length of the plates times the perimeter, or half of the perimeter, and over here is a 2 to be multiplied by 2 for full perimeter. Then we have the total surface area for hot fluid. Same thing, but the inner size, assuming that del is the thickness of the material, which is I hope a reasonable assumption. But when you put it through the calculator in various sizes, you find that it doesn't make a difference in the results. I mean, I'm talking not even 1/100th of a decimal place, because when you're considering thin wall vessels like this, the actual wall thickness plays near no role. Next, there is a hydraulic diameter calculation. Since these are not round tubes, they have to be treated as square tubes. So we have to take a hydraulic diameter calculation there. And then we have another hydraulic diameter calculation here. So the hydraulic diameter for the cold fluid is considered parallel plate flow, because it really can't be considered rectangular because it's so wide. And then the hydraulic diameter for the hot fluid is just considered as rectangular. So those are our 2 numbers there. These are all fluid material constants that were pulled. They are listed as such. You can pause if you want to read through those. They were pulled pretty much from the Changle book, which I've referenced at the end of this document, as well as the Engineering Toolbox website for this one thing here. Okay, next is flow calculations. We're going to look at the cross-sectional flow area of the hot fluid, right? So pretty much length times width times the number of plates. That gives you your total cross-sectional area for the hot fluid. The average velocity of the hot fluid is the volumetric flow rate divided by the cross-sectional area, of course. So the liquid flow through the heat exchanger at the cross-section of plates is approximately 0.03 meters a second. The calculated volumetric airflow rate is here. It's the velocity times the cross-sectional area, and that gives you your 642 cubic feet a minute. Next, we move to the mass flow rate of the hot fluid. This is the crucial one, right? These 2 right here, those are derived from the previous line items using the density. All right, then we move down to definitions of functions. So here we have M and eta, which are calculations that go together to find the functions, the effectiveness of the fins, because there are diminishing returns on lengths of fins. So we'll come back to this, but we will be treating the fins between the 2 plates will be treated as half length with an adiabatic tip, which means there is no heat transfer from the tip of the fins, but that goes back to the fact that we're treating them as half length because they are between 2 plates. This does get treated differently for the 19-row and 25-row dual pass ones, but we won't go over that calculation because, again, it's just the same thing as this, but you just treat the first and last row as full-length fins with non-adiabatic ends. Here is where we actually put the inputs together. So Prandtl number for cold fluid, Prandtl number for hot fluid, etc., etc. We move our way down here, we get all these numbers. Convective heat transfer coefficient for the hot and the cold fluids, M values and eta values for those. Those give us our correction factor for how well the fins actually work. So if you look here, the fins for the cold fluid are 96% effective of their actual surface area, while the hot fluid, they are more along the lines of 55% effective. So then we have the actual effective area, which you have your surface area of the plate plus the correction factor multiplied by the total surface area of the fins, and that gives you your total effective surface area for that fluid. So we have the cold and the hot fluids here. Next, we have the comparator for the cold fluid heat capacity rate versus the hot heat capacity rate. So the cold fluid here is 333 watts per Kelvin, and the hot fluid is 853. This is what I was talking about when I said one is the limiting factor over the other. Well, you need almost 3 times the amount of the cold fluid here, so 3 times the amount of airflow, in order to match this modest water flow that we have going on here. So again, this one was operating at 3.33 gallons per minute, which is very, very low when you consider how fast engines actually flow, which is usually in the 10 to 12 gallons per minute range. All right, obviously the cold one takes precedence as the minimum, so it is used down here for calculation. The theoretical maximum that could be pulled out is 14,000 watts or 14 kilowatts. The actual that was pulled out was 3 kilowatts. So that gives us an effectiveness of Q actual over Q max, 21%. So it is a 21% effective exchanger. Next, we move down to our LMTD calculation. This is where we get the U values. So T1, TH, TL, TH, that's the low temperature difference and the high temperature difference. And then you put it into the LMTD calculator. In your book, you look up your correction factor for the LMTD method. And there's a graph for mixed and unmixed flows. So we look on there, and if we find our position, they pretty much all come out in the upper 90%, so this value doesn't really affect much at all. So here I chose a 0.98 off of the graph, and we got a P&R of that, and by looking at the graph, it comes out, like I said, about an F of 0.98. Then we put in the UA value as the actual Q out, divided by the LMTD times F, and that gives us a UA value of 138.2614 watts per Kelvin. And then you divide by the effective cross-sectional, or the effective surface area of the cold fluid to get the cold fluid U value, which comes out to almost 60. For grins, if you divide the UA by the effective hot fluid surface area, then you end up with a 225. So the secondary check of UA is through the, as we'll say, the long method, which is the sum of all fluids together. So you have your 1 over the heat transfer, the convective heat transfer coefficient times the surface area plus the thickness of material times the cross-sectional area of the material times the K value of the material. So this would be the aluminum plate. Again, this term pretty much does nothing when you change it around because the thickness is so thin. And then this last one is, of course, the cold side heat transfer coefficient for the convective heat transfer coefficient times the surface area. And then all that goes together, and it gives you a UA value of 120, which, yes, that's different than 138, but I was extremely happy to see how close these were together because of all of the experimental uncertainties and such. Those ended up being a lot closer than they were before. I was able to get these values cleared up by clearing up things in my calculator. And then, of course, like I said, we have our UC2 here, which comes out to 51, which is, again, I say pretty close to the 59. At the bottom here, I have my sources. Feel free to check me. All right, guys, so that was a lot of information. I just ran through it in hopes that you guys will go click pause, read through the calculation. If you'd like a PDF copy of it, feel free to drop me an email or drop me your email in the comments and I'll send you over. This is not going to be the end of this series of videos. I'm hoping to be able to do more experimental data, get more experimental results, and then be able to return them back to the community. Thank you all for your support on this stuff. This is really fun because now I get to actually give deliverables and actual quantified data as to the difference between these heat exchangers. And you know, that information is not on the market, so this is new information. That's why I'm so excited about it. And as we found out, that the two best exchangers in the test were the non-traditional ones. The traditional ones showed to be very, very poor in their performance. This isn't to say that, again, one size fits all and you need to get the biggest one possible, but you know, one size does not fit all, and maybe you want to get something that fits your needs. This is to say, from this data, I would definitely say don't just jump to getting the biggest traditional one you can because they're cheap, because obviously we've shown here that just because they're big doesn't mean they work well. It actually has decreased how well they work. But you can also get one of these other style ones, and it has shown through my data that they work exceedingly well in comparison. So again, any feedback is very welcome. I look forward to giving more data in the future. Have a nice day.